So here's another one that we can verify these claims about this area under the curve by checking out a common formula right here. And we look at this shape under the curve of y equals the square root of 9 minus x squared. And we're interested in evaluating the definite integral, that is the region under the curve right here, on the interval from -3 to 3. Well, that is certainly a semicircle. So how do we get that? Well, our area here for our semicircle is always equal to 1/2 of the area of a circle, which is 1/2 pi r squared. Only in this case, what's r? Well, we see that if it's a semicircle, that distance along the x-axis over here from the center out to the edge is 3. And so we'll make our radius 3 right here. And so to get our area, to get our definite integral, we would say that this would have to be the same as taking 1/2 pi times 3 squared. And so we would say that the estimate of this area is 3 squared times pi divided by 2, which is simply 9 pi over 2. As a decimal, that's about 14.14 right there. So we'd say, well, 14.14 square units right here if we were checking. But that is our area under here, and that is the value of our definite integral. So if we're going to be taking definite integrals, we would definitely want to know some properties that are going to help us keep everything straight. And there are a couple of these properties that you should know. For one thing, if we have a function that's defined at the point x equals a, then the definite integral from a to a of f of x dx will equal 0. So we visualize a function defined at the point a, and we say, well, what is the area, or what is our definite integral, the value of our definite integral under the curve just at that point a? And we would have to assume that, well, because this is like a rectangle with no width, this has an area equal to 0. So we say for rule number 1 that the area, the definite integral under the curve, would have to equal 0. Now, the second rule tells us that if f is integrable on a to b, then saying the integral, the definite integral from a to b of f of x dx, it would be the same as taking the opposite of the definite integral from b to a. So if we imagine that we're unrolling this area under the curve from a to b, going left to right, and we get a positive region r as a result of doing that, well, if we reverse the direction, going from b to a instead, we're going to get the negative of that region's value, because we're defining an interval that is going, well, in essence, backwards. So we say that the limits are lower and upper limits. If they go in one direction from a to b, where a is less than b, then it will be the opposite of that interval going from b to a. So we have a positive in one direction, negative in the other.